Okay, question 17. So, the volume of a water tank is represented by a function of the form, and we're given that here, where V is in litres and T is in minutes. Initially means when T is equal to 0, the volume in the tank is equal to 100 litres, and that matches that, so that's not going to be a problem for us. And it is decreasing by 50 litres per minute. So if it's decreasing, it's going down by 50, and litres per minute means that we're looking at a change in volume with respect to a change in time. So this is really like the derivative when T is equal to 0. So we want to determine the time when the volume is decreasing at a rate of negative 50 over 7. Okay, so all we have to do, chug and plug for a little bit. So Vt is equal to AE KT, and we're going to let V equal 100 and T equal 0. So 100 is equal to AE K to the power of 0. So that means that 100 is equal to A. Now this section here will change into 1. So A times 1, so just A is equal to 100. So now we know that our model looks like this. Yeah, model looks like this. Okay, sorry. This is the danger zone in the staff room. So now the next thing that we're going to do is we're going to take the derivative and let it equal this. So let's do that now. So if I take the derivative, we're taking the derivative with respect to T. I hope this means you've run out of cones. Don't throw the scissors. If I die, I'd like this video to be at my funeral. There we go, and we're deriving with respect to T, meaning that this is the one, and this is just like a number in front. We just don't know what that number is. Okay, so I'm going to end up with 100 times the derivative of this will just be K, E, K, T. So dV over dt is equal to, dV over dt is equal to 100 KEKT. And now we're going to use the second fact that we've got, that when T is equal to 0, the derivative is equal to negative 50. So let's just make that happen. Stop it, I'm terrified. Okay. Hopefully this isn't coming across in the speakers too loudly. Okay, there's K, and then T is 0, so we substitute that in, meaning that this whole term at the end here is going to simplify to 1. So I'm left with 100K minus 50. Take the 100 over, and I get that K is equal to negative 2, or negative a half. So now I can restate my model. So our model initially, Vt is equal to 100 E negative a half T, and I know that the derivative of that model is equal to 100 times negative a half E to the power of negative a half T, and then I can simplify that later. Okay, so now the next thing that we're going to do is we want to determine the time when the volume is decreasing at this rate. So if we're decreasing, that means we're going to let dV over dt equal negative 50 over 7 when T equals, that's the thing that we're going to find. Okay, so negative 50 over 7 is equal to negative 50 e to the power of negative a half T. Okay, when I take this across, it'll divide, so it'll end up on the bottom here like this, meaning that this one will cancel that one, and I'll be left with 1 over 7 is equal to e to the power of negative a half T. Okay, now I can take e across by using my natural log. So natural log 1 over 7 is equal to negative a half T. So when I take this to the other side, it'll invert the fraction. I'll end up with negative 2 ln 1 over 7 is equal to t. So if you're not sure what I've done there, I've taken the 2 across by timesing, and then I've divided by negative 1, and then I've simplified this to be that. Okay, so now I'm going to take this back up the top over here as a negative power. So now I've got ln 1 over 7 to the power of negative 2. So this power will hit both parts of it. So ln 1 to the power of negative 2 over 7 to the power of negative 2. Now to make these have positive indices, all I have to do is flip the fraction. So it'll become ln 7 squared over 1 squared is equal to t. 7 squared is 49 over 1 squared is just 1. So that'll simplify to t equals ln 49.